Hello, dear student friends. So we are having a break from Monday due to COVID-19 pandemic. We are just three lectures short from finishing the syllabus of complex analysis 2, and I'm not sure now whether we'll get any chance to finish those three lectures or not. So here is my attempt to reach you out through this video slideshow, and depending on your feedback, I'll continue to make uh, this more of these lectures. So let us try to cover whatever was remaining. So we start by recalling the definition which we have seen last time in the class, probably on Saturday, which was definition 5.10 from Conway. It's about elementary factor. If you recall, we have defined elementary factor as those functions EPZ for p non-negative integer. So for p equals to 0, we have E0Z equals to 1 minus Z, and for all other p greater than equals to 1, we have EPZ equals to 1 minus Z exponential of this finite sum z plus z square by 2 plus and so on z power p by p. So some remark about this functions EPZ. So EPZ by a, if you replace z by z upon a here, then we have EPZ by a equals to 1 minus z upon a exponential z upon a plus z upon a square by 2 and so on z upon a power p by p. So uh, this will be an analytic function, and when it has a 0, it has a 0 at z equals to a, 1 minus z upon a. So if z equals to a, 1 minus 1 upon a, which is 1, so that it's 0, and this part is never vanishing for any z exponential. So it has a 0, only 0 of order 1, so it has a simple 0 at z equals to a and no other 0. And now suppose the domain of EP is an open set G. So G to C, suppose EP are functions from G to C, and if B is not a point in G, that is if B is a point in C minus G, then again just similar to this one, EP of A minus B upon Z minus B. This will also be an analytic function because Z belongs to G and B is not a point in G, so there is no problem. And it will also have, just from the previous remark, you can say that it has a simple 0 at z equals to a, because at that we'll have a minus b upon a minus b. So 1 minus a minus b upon a minus b, so that will give a 0 at z equals to a, and this is analytic on G. And if we consider G equals to C, then EP from C to C, they are entire functions for all P, as you can see. So these are just two remarks about EPZ. And now the next lemma which we are going to prove in the next class, so we'll try to cover here. So that is it's just a bound on this 1 minus EPZ. So if mod z is less than equals to 1, then for all p greater than equals to 0, 1 minus mod of 1 minus EPZ, that is less than equals to mod z power p plus 1. So the proof is simple. The first case, for p equals to 0, mod of 1 minus EPZ equals to 1 minus, we put p equals to 0, so 1 minus E0Z. This equals to 1 minus, and recall the definition of E0Z, that is just 1 minus Z. So this is nothing but mod Z. We can always write this is less than equals to mod Z, and so mod Z power 0 plus 1, where p is 0, so we can write mod z power p plus 1. So for p equals to 0, this inequality is trivial, right? And so now we move for the case where p is greater than equals to 1. So for fixed p greater than equals to 1, as we discussed earlier, EP from C to C, this is an entire function, so it will have a power series representation. Let us say about z equals to 0. So let EPZ equals to summation k equals to 0 to infinity ak z minus 0 power k, so z power k. be the power series expansion of EPZ about z equals to 0, where AK we know, AK, they are the Taylor coefficients, right? So because it is entire function, so it has power series representation. And by definition, what is EP0? Substitute z equals to uh, 0 here. So EP0, that is nothing but it is just 1 in the definition. If you see EP0, this is 1. So the left hand side is 1, and here if you substitute z equals to 0, we get the constant coefficient A0. So what we can conclude is A0 is 1, and therefore this power series expansion we can write as EPZ equals to 1 plus the constant term, we take it out, A0, so 1 plus summation k equals to 1 to infinity AK z power k. Right, so we have this power series expansion of EPZ about z equals to 0. And so if we differentiate this, because they are entire function, so EP dash z equals to summation k equals to 1 to infinity AK, and then k z power k minus 1. So we call this star because we'll be using this later. So EP dash z is this in the terms of power series expansion. And on the other hand, if you use the definition of EPZ, that is p equals to 0 case we already done. So we recall the definition where p is greater than equals to 1. It was defined as EPZ equals to 1 minus z exponential of this finite sum. So from this definition, if we compute EP dash z, so EP dash z, so that is we use a product rule for differentiating this. So 1 minus z will give us derivative minus 1 and exponential of this as it is, then plus 1 minus z as it is. Now we differentiate this term. So what is derivative of this? This is nothing but exponential of this is as it is, and we have to differentiate this. So by chain rule, z, this derivative of this will be 1 plus 2z by 2, so that will be z. Then again, so this will be 1 plus z square up to pz power p minus 1 by p. So p get cancelled, so z power p minus 1. Right. And so next step, we write the first term as it is. This is just simplification. We write the first term as it is. And the next term, so you observe this is expansion of 1 minus z power p, just a factorization of 1 minus z power p. So this is 1 minus z power p exponential of this as it is. And so now taking minus sign common, so 1 minus 1 minus z power p exponential of z plus z square by 2 plus up to z power p plus z power p by p. Yeah, so this is nothing but this will give us EP dash z minus z power p exponential of z plus z square by 2 plus up to so on plus z power p by p. So this is EP dash z using the definition, and we had also EP dash z using power series expansion. So if we compare the two expression, that is the power series expansion of EP dash z and the definition, we have this. So this summation k equals to 1 to infinity k ak z power k minus 1 equals to minus z power p exponential of this. And now let us expand this. So minus z power p exponential of this. So there might be some typos in my notes which are to be corrected. So e raised to z, so 1 plus z plus z square by 2 factorial plus and so on. It's just to observe that if you multiply z power p inside, so this is z power p, and all these coefficients will have power raised by p because z power p is multiplied inside. So z power p into z power p plus 1, z power p plus 2 by 2 and so on, and plus z power p by 2 factorial and square of this and so on larger terms. So the comparison of this two, we can say two things about the coefficients ak. First of all, note that what is a constant coefficient here. If we put k equals to 1, then we have z power 0. So we have a1. A1 is the constant coefficient. When we put k equals to 2, we have 2 a2 z, and then 3 a3 z square and so on. But here there are no coefficients of, there are no constant terms, there are no, the smallest coefficient is z power p. So for k equals to 1 to p, we have z power p minus 1. So those coefficients are 0 because they do not appear here. So this is the first observation, that a1, a2 and so on up to ap, these are 0. I hope I'm not going too fast. Just take your time and observe this. Because since it's a video, you can pause it as well and then continue when you are ready. It's not like the lecture. And the second observation, you observe that for all other coefficients p plus 1, k equals to p plus 1, we have z power p. So from z power p and higher powers, all the coefficients in this bracket are positive, but there is a minus sign here, and therefore ak, all other coefficients where k greater than equals to p plus 1, they are either less than or equals to 0. So these are the two things we observe. First, p coefficients are 0 and rest other coefficients are not positive. So because ak is less than equals to 0 for k greater than equals to p plus 1, we can write mod ak as minus of ak for k greater than equals to p plus 1 because they are negative. So this is definition of modulus. Mod x is x if x is greater than equals to 0, minus x if x is less than equals to 0. So for z equals to 1, since the first p coefficients are 0, and so this gives ep of 1, put z equals to 1 in the formula. So ep of 1, that is 0, and then this is 1 plus, recall the formula of epz, 1 plus summation k equals to 1 to infinity ak, and then z equals to 1 here. So this is just summation ak. And so this sum for k greater than equals to p plus 1, so k greater than equals to p plus 1, so mod ak, this is nothing but minus ak, so we have minus summation k equals to p plus 1 to infinity ak, and previous p's coefficients are 0, so here also this sum equals to nothing but minus of this. If we take on the other side, we have just, it is 1 plus summation k equals to 1 to infinity ak is 0, but these are 0, so anyway this sum starts from p plus 1 only. So summation k equals to p plus 1 to infinity ak, minus of this you take other side, so that is nothing but 1. So this will be using, so remember this, this sum is nothing but 1. So finally for mod z less than equals to 1, whatever we wanted is 1 minus epz, 1 mod of 1 minus epz, which is nothing but mod of epz minus 1, which is mod of, put the expansion of epz, 1 plus actually k equals to 1 to infinity akz power k, but previous coefficients are 0, a1 to ap, so the sum starts from k equals to p plus 1 to infinity and then minus 1. So 1 gets cancelled, so this is mod of nothing but summation k equals to p plus 1 to infinity ak z power k. Now take z power p plus 1 outside, so we have this power is reduced to k minus p minus 1. So z power p is just taken outside, so we have mod z power p plus 1, sorry, mod z power p plus 1 outside here, and so this is less than equals to mod z power p plus 1, and this is mod of ak, mod of z power k minus p minus 1. But we have mod z is less than equals to 1, therefore this is just less than equals to mod z power p plus 1, and then summation k equals to p plus 1 to infinity mod ak. Now here we use that triple star, that this sum is nothing but 1. Because this sum is 1, this is just mod z power p plus 1. And this was the desired inequality which we wanted to prove. So this lemma is proved, and this will be used in the next result, this inequality. If depending on your feedback, I will try to make another video if this was good for you to understand. Otherwise we'll wait for the classes to begin, or let us see at least what happens. Thank you.